Hi everyone, Big Mac here. It's been a while since I did a math video, so I thought I would give a brief idea to the introduction of proof by induction. So introduction, induction kind of sounds the same. I'll go over the basic parts of what's going on in this particular idea of proving something to be true. This kind of thing is sometimes seen in a high school pre-calculus class. Otherwise, it might not be seen until introductory analysis classes in college, like the classes that math majors would take. Something like that. But in fact, the idea of proof by induction is a pretty straightforward idea, so I'll just quickly describe what's going on. There are three basic steps that we'll be going through, and we'll show some examples of how that works in each particular case. All you need for this kind of a topic is the idea of a strong algebra skill, so being able to factor divide. Obviously, I'm just using more basic cases involving algebra notation, so hopefully you guys have strong enough algebra skills for that. And the knowledge of summation notation is definitely useful, but not critical for this particular lecture that I'll be giving you guys today. So, what is our motivation for the idea of the method of induction? So suppose one day your friend claims that she found a formula that can add up the first capital N positive integers, whatever that number happens to be. She says that if you just take 1 plus 2 plus 3 plus 4, etc., all the way to n, your whatever that number happens to be, if you add them all up, that in fact you can find this by just by evaluating n times n plus 1 and then dividing that whole thing divided by 2. In summation notation, this can be represented over here. What we have here, we have the expression of I, starting from I equals 1 up to capital N. So again, this just means when I equals 1, you evaluate this thing for 1. When this thing is 2, you evaluate this thing when it's 2. When this thing is 3, etc., and then you just add them all up together. So this thing over here, the summation notation, again, just the same thing as adding 1 plus 2 plus 3 plus 4 for this particular example. But anyway, so if you just add them all up, you can, that might take a while, especially if you go through it one step at a time. But if you could just multiply everything together, that would be pretty cool. So you test it out on a couple of cases, and it seems to be working. Of course, just making sure that it works in a couple cases is not enough proof that it will always work. So what we want to try and get an idea of is how to prove that it will always work, especially if we're working with things like integers or whatever kind of a special case that we have going on here. So we get the idea of proof by induction. There are three basic steps that we go through for every example. One, we make sure that it works for a very simple case, usually the easiest case possible. We assume that it'll work for a particular case, so it looks like what we want to prove, but that's just part of the induction process. And then, in order for it to be an inductive thing, we basically have to prove that it will work for the next particular example. So let's see this thing in action using our summation formula notation. So, step one, like I already said, make sure that the formula or the rule is going to work for a simple example. So by default, proving it true when your n is 1 is always sufficient. So it might be a little trivial at that case, but if you're not convinced, feel free to show that it works for n equals 5, n equals 10. So really quickly, let's show off that this summation works for n equals 1 and n equals 5. Well, the sum of the first number is just 1. So if we were to actually plug in n equals 1 into that formula, we had n times n plus 1 divided by 2. So 1 times 2 is 2. 2 divided by 2 is 1, and so 1 is 1. That's a good start, so it works for our simplest case. And if we had n equals 5, we went 1 plus 2 plus 3 plus 4 plus 5 adds up to 15. So let's try using that in the formula. N is 5, 1 more than that is 6, so n times n plus 1, we get 5 times 6 divided by 2. 5 times 6 is 30, or you can think of it as 6 divided by 2 is 3, so you get 5 times 3. Either way, you're getting to 15, which is the exact same thing as before. So it seems to be working. For step 2, we assume that this is in fact going to hold true for some arbitrary value. I'm using the variable k, but it could be anything that you guys, it could be anything that you choose in particular. So obviously this looks like what we want to prove, But now what we're going to have to do is use this to prove that the thing works in the very next case. Because so we assume that this is true up to the first k integers in this case. So now our final step is we need to see if it holds for the k plus 1th iteration, the very next one. Because if it works for the very next one, even in an arbitrary case, and we've already proven by our basic example, when we just started off with our case of 1, k equals 1 or capital N equals 1, so if we can prove that it will always work for the next case, then since we already proved it works for 1, it'll work for 2. If it works when k is 2, it'll work when k is 3, because we've already done that proof by induction. So if you give me a number, we've already proven that it will work for the next number up. So then that means it'll just keep being correct and go on forever. So how do we utilize this into our particular notion of summation notation? So we want to prove that some of the first k plus 1 numbers, I'm just using our summation notation, is we want to see if it's the same thing as if we had just plugged in that particular value into our formula. So again, we normally have n times n plus 1 over 2. But now that we're adding k plus 1 numbers, we plug that whole thing in. So this term is k plus 1. This term is k plus 1 plus 1, or just k plus 2. So we need to try and find a way to add up the first k plus 1 numbers and see if in fact it equates to k plus 1 times k plus 2 divided by 2. This is where our assumption from step 2 is actually going to come into really big play. So again, by following our summation notation, we said that we were just adding up the first k plus 1 integers. Well, that's the same as just adding the first k integers and then just adding the next one, isn't it? I mean, we could break it up into however we want to sum these things, but adding up the first k plus 1 numbers is just the sum of the first k plus the very last one. Well, if what we assumed was true, and if what we're trying to prove is true, then we know that the sum of our first k terms has to be k times k plus 1 over 2. So we've already compacted the sum of all of those numbers into what we hope to be true. We, of course, are now adding that very next number. So note here that I'm using a little bit of algebra in this case. You could do some different things like combining it all to the same fraction or whatnot, but it should all work out the same way. So what I noted here was that we have a k plus 1 term here and a k plus 1 term here. I actually factored that k plus 1 term out from both parts. So what's left is k over 2 from the first bit, and then since I factored out the whole k plus 1, it's just a plus 1. There's just a 1 term left over, so we have k over 2 plus 1 from out here. So of course, adding 1 is the same as adding 2 halves. I just figured that would be easiest to make it a common denominator here. So k over 2 plus 2 over 2 becomes k plus 2 over 2. And from there, like our algebra was hoping, like we were hoping it would, in fact, the sum of the first k plus 1 numbers becomes k plus 1 times k plus 2, all divided by 2. So in fact, this is the end of the proof. We have proven that this thing will work for the sum of the first capital N positive integers. We have proven that this formula will always work. So yeah, your friend was right. So of course the two of you go and show it off to all your friends and teachers, because your friends and teachers are really cool. But anyway, here's our second example. So, this time you show off something to your friend. You show off a formula that the sum of the positive divisors or factors of some power of 2 to the n, you say that if you add up all of the factors, then that is 2 to the n plus 1 power, and then just subtract 1. So that seems a little convoluted, but she doesn't believe you, but you try it out in a couple of cases. So let's look at a particular one here where we have 2 to the 4th being 16. So in this case, n is equal to 4. So what are the numbers that divide into 16? Perfectly, we have 1, we have 2, we have 4, we have 8, we have 16. So that seems to work out pretty well for us. So in fact, if we were to add these things up, so 1 plus 2 plus 4 plus 8 plus 16, we get 31. Well, that doesn't seem too interesting. But if we look at the very next power of 2, after 2 to the 4, we would get 2 to the 5th, which is 2 times 2 times 2 times 2 times 2, which is 32. Well, 31 is 1 less than 32. So again, when we had n equals 4 for our 16 case, in fact, adding them all up gave us 2 to the 5th minus 1, 5 being 1 more than 4. So again, your friend tries it out on 64, which is 2 to the 6th power, finds all the divisors, adds them all up, and in fact it is 1 less than 2 to the 7th power. So what's going on here? Obviously you guys want to try and prove that, in fact, this will be the case as well, so we're going to use the notion of proof by induction. So in fact, it's going to follow the exact same format that we had before. There was step 1, make sure it works for n equals 1 and for trivial cases. Step 2, we assume it to be true. Step 3, we work it out, hopefully with a little bit of algebra magic, and we make sure that everything does in fact pan out correctly. So, does it work when n is equal to 1? Well, 2 to the 1st power is 2. So the factors of 2 are just 1 and 2. So those add up to 3, which is 1 less than 4, which is 2 squared. So yes. So when n equals 1, the sum is 1 less than 2 to the next power up, being 2. So again, we're going to assume that this thing is true for a very arbitrary value k. So we're saying that the sum, I found a nice way to describe all of the factors, or all the divisors of 2 to the k, are in fact all the other smaller powers of 2, right? We said 1, 2, and 4, and 8. We're just repeating the powers of 2, because they're all the factors of the bigger number. So in fact, using summation notation, I'm just going to say that the sum of 2 to the I, again, now notice here that it's getting a little careful. We have to be a little bit careful here with our counting. From I is equal to 0 up to k. So again, thinking about our early example, when n equals equal to 1, we still had 2 factors. When n was equal to 4, we had 5 factors. So the fact is, when n is equal to k, we're going to have k plus 1 factors. So if you start at 0, 1, 2, 3, 4, all the way to k, that accounts for all k plus 1 possibilities. So anyway, adding these things up, it should be equal to 2 to the k plus 1, and then subtract 1. So let's go ahead and do a little bit of work, see if this is in fact true. So of course we want to prove that for the very next case, that if we add up all of the first k plus 1 powers of 2, then we should expect this thing to be 2 to the k plus 2 minus 1. So let's go ahead and work that out. And again, like before with our summation notation, we can break up this sum into all the previous terms plus the brand new term. So we did that just here. So we have our sum of up to k, and then our very next term as well. By our assumption, we already know what the sum of the first k, what that first part of the sum is, 2 to the k plus 1 minus 1. And then in fact we're adding another term of 2 to the k plus 1, because 2 to the k plus 1 divides into itself. So in fact we have 2 terms of 2 to the k plus 1. So that's 2 times that. So of course our general properties of exponents come into play now. And 2 times 2 to the k plus 1 is 2 to the k plus 2. And of course we still have that subtract 1 from before. So that is exactly what we wanted it to look like. So in fact we're done. So again, some of these examples are pretty straightforward. They can be quite convoluted. Again, I'm just trying to show more basic algebra proofs at this particular video. But let's go ahead and look at some more examples that if you guys feel like trying. So what I'm going to do is I'm going to briefly discuss some of these exercises. Feel free to pause the video. Feel free to go do something else. And then come back maybe here and check out the video later. So these are just 2 sample problems that I thought would be worthwhile going over. So number 1, show that the sum of the first n odd positive whole numbers is n squared. So let's just think of an example. We take the first 3 odd positive whole numbers, which would be 1 plus 3 plus 5. Well, that's 9, but that's 3 squared. So how can we use our notion of proof by induction to prove that the sum of the first n odd positive whole numbers is, in fact, n squared? Especially if you try and write this using summation notation, try to make a nice formula that allows you to describe what the nth odd positive number is as you're going through the summation. That's my hint for you guys on that part. Our second problem, show that the sums of the squares of the first n positive integers, so I'm saying 1 squared plus 2 squared plus 3 squared plus 4 squared, etc., up to some capital N. So the sum of those first squared numbers is can in fact be given by this formula. We have n times n plus 1 times 2n plus 1, all divided by 6. So feel free to go through the 3 steps. Make sure I know it may seem silly to try and do that first step, but believe me, in order to do a formal proof by induction, you actually do have to include all 3 steps. So go ahead and think about that for a little bit. I will see you guys in the next part.